Fenomenal.
Aquí está tu hermano.
¿Dónde estás, Ana? ¿Estás en tu casa o estás en otra parte?
No, no, estoy en el trabajo. Estoy en el trabajo. Me he quedado para no tener problemas de conexión de tal, de cual, pascual. Digo, bueno,
¿Qué hora y son las 6 de la tarde ya,
Son
no?
las 6 de la tarde, sí.
son las 6, sí.
Sí.
Este fin de semana nosotros cambiamos la hora, así que pasamos a 5 horas.
Sí, sí es que, sí, lo que, vamos, me había puesto, digo, a ver si hay cambio de hora y tal, y he buscado en internet, hora en Santiago de Chile, y me ponía que había una diferencia de 6 horas. Digo, qué raro.
Así es.
Bueno, no sé.
No, después
Y nada,
pasamos a 5 y para Navidad ya estamos con 4. Ustedes cambian, no sé
ya,
qué cambian ustedes.
A fin de octubre probablemente cambian ustedes, ¿no?
sí, nosotros cambiemos, no sé exactamente, la verdad es que soy un desastre para lo de la hora, pero
No, pero siempre es el último fin de semana de octubre en Europa.
sí,
Sí.
más o menos.
Ellos son ordenaditos, nosotros somos los desordenados. Cambiamos todos los años, entonces el despertar se arma con los sistemas computacionales que ni te cuento. Oye, Ana, muchas gracias por aceptar esta morada.
Anda ya, a
Hemos
vosotros.
estado persiguiendo hace días para que
Sí,
para este seminario.
sí, no, no, si es que encima ha coincidido, he tenido campo, he tenido salidas, o sea, he estado desconectada, en fin, pues eso, el lunes a las 7 de la mañana me voy a Bonn.
Y nos vamos a ver a las 2 de la tarde entonces.
Sí,
¿Ah?
sí, 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 porque llego a Colonia a las 12:30. Entonces, aunque sea, me siento allí en algún sitio con el ordenador y me conecto
Muchas,
desde donde sea.
muchas gracias.
Así que nada, no hay problema.
Si quieres, bueno, no sé, dependiendo no, está bien, las 2 de la tarde tuya, que van a ser las 9 de la mañana, mía está perfecto. Oye,
Vale.
Ana,
Me-
tu cámara no está prendida, ¿es intencional o simplemente?
No, no, es que no me sale.
Ah,
Sí, es que es lo que estaba mirando. Digo, qué cosa más rara, porque siempre sale con esta.
¿no puedes habilitar la cámara? No puedo habilitar su cámara, porque eso es como parte de su computador.
O sea, tienes problemas, no te reconoce la cámara.
No, no, sí, que si nunca he tenido problemas de reconocimiento de cámara. Si es la primera vez que en Zoom me sale como si estuviera, como si fuese asistente.
Ah,
Entiendo que debe ser eso igual.
lo voy a buscar al técnico.
Pero no está, ella no
Mm,
está como, dice que todavía no está con...
Sí, sí, está como cojos.
¿Sí?
Sí.
A veces está como...
Déjame,
Está como coanfitriona, me dice. ¿Qué tal tus vacaciones o ya te olvidaste de lo que fueron?
Jo, me olvidé hace tiempo. Ya, ya además la vuelta ha sido súper rock and roll, vamos.
Ya.
Ya ha tenido pues mira, nada, o sea, al poco de llegar, bueno, qué demonios, al poco de llegar, bueno, tuve una movida tremenda, pero cuando parecía que ya las cosas empezaban a amainar,
¿Mm?
me contactan un lunes por la tarde para montar una propuesta de corales. O sea, nos contactaba un consorcio que era saudí y egipcio
¡Ostras!
para montar un tema de monitorización de corales en toda la costa de Arabia Saudí, en el Mar Rojo y tal.
Ahí hay pela, ¿eh?
Bueno, sí,
¿Eh?
bueno, pero es que he descabellado completamente, ¿eh?
El
O
tiempo,
sea,
la pela es la pela.
no, no, ya, pero vamos, o sea, era una cosa absolutamente descabellada, porque le habían montado de tal manera que lo que pretendían era hacer la monitorización de todo el sistema utilizando el WorldView 2.
Perdón, Ana,
Dime.
Ana,
Sí, sí.
ya estamos transmitiendo, entonces, ¿tú
Ah,
puedes mostrar tu presentación o también
sí, a ver.
la voy a ascender a panelista porque no estaba como
Ah,
panelista.
sí, eso es, eso es.
Un segundito.
Volverá a entrar al seminario como panelista.
Ahora sí
Ya, ahora
tienes,
sí va a poder entrar su. O sea, encender la cámara.
ahora puedes presentar.
Sí, pero me dice que no puede iniciar su vídeo porque el hospedador lo detuvo.
Espera un momento.
Sí,
Anfitrión y. Inténtelo ahora.
vamos allá. No, me sigue diciendo que no puede iniciar su vídeo porque el hospedador lo detuvo.
Es que acá, mira, aparece ahí.
Ah, ¿lo parece ya? Ah, ok. No estaba viendo la pantalla. ¿Y ahora?
¿Ahora?
Vamos allá.
¿Eh?
Ahora sí.
Ahí sí. Bueno, muchas
Iba
gracias.
yo que me he puesto de amarillo para animar un poco, porque encima aquí ya se ha metido el otoño, hace un frío espantoso. Así que
En fin, oye,
Florencio.
¿puedes poner tu presentación?
sí, voy a poner compartir pantalla, opciones, varias partes. ¿Por qué no me ahora? Perfecto.
Ahí sí.
Ahí, ¿no? Vale,
Perfecto, listo, Ana. Bueno,
estupendo.
para aprovechar a la gente que está en línea también, quiero presentarte. Bueno, tenemos hoy
Vale.
el gusto de tener a Ana Silió-Calzada, que es investigadora del Instituto Hidráulico de Cantabria y una gran amiga de la casa. Nos va a presentar va a hacer una presentación sobre eh, una visión de los sistemas acuáticos vistas de la percepción remota. Así que, Ana,
Solo una cosa, bueno, la presentación la tengo hecha en inglés,
¿cómo es esto? Bueno,
pero me da igual, o sea, me da igual hacerla en castellano, lo que vosotros prefiráis. O sea, porque como en un principio pensé que
ahí,
eso con lo que habíamos hablado, me da exactamente igual. O sea, hacer el switch al castellano.
habla en inglés más, habla en inglés.
Vale, vale, pues empezamos.
Adelante, Ana. Thank you.
Um, Good evening or good day, everyone. I'm really happy to be here presenting, having this opportunity of presenting a slide insight about how remote sensing might be applied in order to monitorize the aquatic ecosystems. So this is part of some of the things that I'm going to show you are part of a research that I carried out some time ago, but well, they are part of my work and my delight. And I'm an aquatic and remote sensing scientist or aquatic. Yeah. So this is part of it, and I hope you enjoy it. So as I don't know what's what's your level of knowledge about what's remote sensing or what we're talking about, I'm just gonna introduce some general ideas of what remote sensing is and what are the basics of what is this technology or this compound of methodology and technology and data that we use in order to obtain these or to perform this type of studies. So the first thing is, well, remote sensing is the science that encompasses all the techniques and processes and formulations that are necessary to acquire the information about farther away targets. I mean, so what we do is what we obtain information about things that are without touching them. So the first remote sensor that we all know are the eyes, but we're going to deal with something that is a little bit more complex, that are the satellite sensors. So this is basically what they do, and the physics that are based on, and this is specifically the optical remote sensing, are just, well, they are based on the reflection of the water, of the pardon me, of the incident sunlight that is reflected towards the satellite sensor. So what we obtain is just what is being illuminated by the sun. And what we do is we collect that information at different spectral bands. So it contains information of very specific spectral ranges. And basically, why do we use this? No, what's the purpose of it? Well, basically, it's to obtain periodical and systematical data. It allows us to acquire data over large areas of information that are farther away or remote, or with not an easy access. And it provides us with long-term repositories of data, which is fantastic in order to be able to analyze what's been happening for the past 20 odd years, even more. I mean, in the case of Landsat, we're dealing with almost 40 years. So these specific data and techniques and formulations and processes and so on are really widely used in terrestrial and aquatic ecosystems. So the combination between these techniques and the data obtained linked to in situ data allows the development of geospatial analysis that are key in order to answer very specific questions that are asked in terms of the environment or the climate or whatever. No? So in the immediate where we live. So I'm going to focus, as we're going to deal with water bodies. I'm just going to focus on the water optics. And why? Well, because they are an important tool for monitoring this type of ecosystems. They provide us loads of information. Because, well, why is that? Is because the water optics is linked to the study of the propagation of absorption of the light in the water, within the water, and how it is, and how this light is used and measure is used for measuring the water characteristics. And why is that? Because it's linked to the optical constituents, optically active constituents of the water, which are basically, I mean, in a very rough simplification, there are the chlorophyll concentration, the turbidity, and the water depth. So water optics is a very multidisciplinary field, as it requires the coupling of the physics of the light, how the light is being transferred from the surface along the column, the water column, and then back towards the sensor, and the biological effect of the energy sorry, being absorbed and scattered within the water column. So when we deal with water optics, we talk normally what we talk is about watercolor. And as I was saying before, is the result of three main components of constituents, in addition to the water per se, the water matrix. That is the dissolved organic matter, which is one of the most complex compound, because you can say dissolved organic matter and you're really saying nothing, because it's the combination of all sorts of humid acids, fulvic, and it varies from one place to another in the earth. The non-algal particles, which is also called the suspended matter, or the total suspended matter, and the chlorophyll A concentration, as that is used as a proxy of the phytoplankton biomass. So these are like the three main components towards everything turns around. So in order to study the water optics, what we focus is on the spectral signature of the water. And it's exactly the result of a very of an antagonistic effect between the absorption of these components of the light and the backscattering. So the higher the absorption, the lower the observed reflectance. And the higher the backscattering, the higher the reflectance is. So it's just a balance between it. And everything, all these three constituents, they have very specific regions in which they carry out this absorption and backscattering. So as well, to carry on, the magnitude of the reflectance or the spectral signature is conditioned by the concentration of the amount of constituents that you have. So, well, this is just a resume of what's happening in the water. So I'm not gonna go through all the formulation, the mathematical formulation, but this is basically what we as water optic scientists, we think first, we either think that first in terms of the concentration of the constituents, and then the water reflectance, or the reverse. So this is basically the graph. So, well, this is just to illustrate how the watercolor changes. And it changes because of these differences in the concentration of the constituents. And as you can see there, I'm not sure, can you see my pointer? Yeah, good. There are specific regions within the spectral where the constituents, they have a higher action, or they are more characteristic. So, for example, in the blue, there's a really high absorption of due to the dissolved organic matter, and this is going to affect well, basically what the color is. If we don't have reflectance in the blue, well, the water is not going to be very bluish, but something in between, something like a greenish, even brownish. So it's the higher the concentration of the dissolved organic matter, the closer the water seems like tea, like an infusion. a brown infusion of things. In the case, well, in the case of the pigments, there are different regions in which they affect the most, and we focus basically on the absorption of very specific zones in which the fluorescence happen, and this is this also provides us the amount of activity that it's happening, like the biological activity that is happening within the water, like primary production and so on. And in terms of the solids, well, the suspended solids, they don't really provide they don't really provide absorption, but scattering, and they scatter all over, and they provide an enhance of the signal. So this is just these are just very brief samples of what I was saying. So this is just to illustrate what I was saying, that the absorption is really high. For example, in the water, the pure water, the maximum absorption of the pure water is around 750, more or less. So it is accepted that the water, all the signal that you get from the water that is beyond 750 is something that is not water, but the surface effects and I don't know, the scattering of the suspended matter or so on, but not really what the water per se is providing information. So in the case of the serum, as I was saying, for example, this is super high in the blue, and it decreases exponentially, and then the chlorophyll, it varies a bit. So this is just like a very average behavior, because obviously, I mean, we deal with chlorophyll A, but there are many other pigments that affect the signal, right? And in the case of the backscatter, well, what I was saying is that, as you can see, the most of the backscattering is provided by the suspended matter. See?
Can I make you questions?
Yeah, sure.
Why you are considering all your graphics between 400 and 800? The information which go
Yeah,
900,
yeah,
there are advanced of Sentinel-2. Why
yeah.
on that? There is no
No,
information, or there is something special?
the thing is, yeah, it's a very good question. This is something that is just accepted by the ocean color community or the watercolor community, that it is considered that everything that is beyond 800 is just related to surface effects of the water. So it's something, or even atmospheric effects or whatever, but it is not going to provide a reliable insight of what's happening in the water. But this is an assumption for ocean color scientists. In the case of dealing with fresh water, this is something that you cannot do. I mean, I'm just showing this because these are the curves that are typical, and I'm not sure they provide for the further data beyond beyond 800. But in reality, when you deal with freshwater or coastal waters or wetlands or the media that is a lot more complex that the open water. You have to consider what is beyond those 800, because you have floating algae. You have emerge plants. So some of the, for example, in the case of the in between the water body or the lake, and this is an example that I'm going to show that is it's in Brazil, in a really huge lake. There's a wide in between the open water, what is considered the lake per se, and the land, the pure land. So it's all the wetland, and you need the infrared data that is not going to be assumed by the super snob water scientists that we are the worst when we don't consider vegetation. That's why.
Thanks.
So basically, these curves, they vary a lot in terms of depending on the size of the particles and the nature. What I was saying about for example, in the case of the sedum, I mean, it's not the same that if you have more humid acids or fulvic acids, because I mean, the composition is not going to be the same. So the characteristics of the water are really going to vary. So this is just an assumption. It's an example. So, for example, this serves us to illustrate this graph, to illustrate the difference. For example, in here is related to the phytoplankton absorption, but the difference between this dash curve and the green one is basically the size of the phytoplankton. So it's going to have an impact. And then on the other hand, in this one, for the same type of phytoplankton, what they did was just to vary the concentration of it. So it's just to illustrate how things change and shift, and they get really complex. That is feasible, is doable. So yeah, this is another example regarding this is also spectra that has been simulated, and so everything seems like super clear and but reality, it gets a lot more messy and complicated. That is the fun of it as well. So another thing that is super important in the case of the water is the bottom effect, because of different things. If we're dealing with the water body, and if we are interested on measuring or estimating the water quality of the water body, what we need is just the information of the water column, not what is underneath. On the reverse, if we're dealing with, if we want to know what is in the benthos and the benthic layer and the habitats that they live on it, we need to be aware of it, and the quantity of the water column that has to be removed from the signal in order to retrieve that supposed signal that it's coming from the bottom. So the bottom, as you can see, it has an important effect. From the A, there are the macrophytes. And you can see in here that is I mean, this is vegetation. You're dealing with water, but the shape, the spectral shape of the curve is vegetation purely. To dark silt, which is something. I mean, the spectrum in here is it's difficult. But you can see, well, in these ones, we observe the differences between, well, this is the combined effect between the depth and the type of benthos that we're dealing with. So, well, I'm not gonna go farther, but just like the take-home message from it is that the deeper the depth, I mean, the smaller the effect of the benthos. And this sounds like really obvious, but it's something that you have to be extremely aware, because some of the approximations that we use for estimating, I don't know, different coefficients, the extinction of the coefficient related to the extinction of the light, is based on optically deep water. So you have to make sure that you're taking pixels, the reference pixels are the ones that are really far away and where the bottom effect is negligible. So the approximations, or what I was telling you before, is they are different in terms of in function of the type of water that we're dealing with. For example, like the most easy, or I wouldn't say easy, but the most straightforward type of water is the case 1, and it's the one that is where everything is related. So your chlorophyll concentration is related, or excuse me, no, your sedum is related to your chlorophyll concentration because it's just a product of the decay of the phytoplankton. And you don't have suspended matter, and the only matter that you're going to be suspended, that you're going to have suspended, is just phytoplankton. So everything is nice and straightforward, but unfortunately, this only happens in the open ocean because and in very specific regions, because for the rest of the cases, everything is a lot more complex. I mean, all the influence that the coast or the external influence that you can have along a lake or a reservoir or whatever are going to make those relationships between the constituents not straightforward. So, as I was saying, I mean, in the type 1, we know, well, this absorption and the scattering are correlated. Everything's cool. But in the case of the type 2 waters, those correlations are not clear because you have all sorts of external inputs, and is where, well, we have to think quite more deeply about the way to retrieve all the variables that we might be interested in. So, well, this is just another example of the type of water, the spectral signature link to the different types of water. I mean, these are very classic ones, are the blue waters, basically. I mean, the ocean is just perfectly blue. You have barely no signal in the infrared. Everything rules. Everything's fine. The fjords are fairly pristine, so the water is really nice and you have no external sources. Whereas in the case of the estuaries or coastal, things get a lot more complicated. And inland is just another level of complication. So one thing that we can do in order to know about the type of water that we're dealing with is just a very simple approach, and is something that is based on spectral ratios, how the reflectance performs at different spectral regions. And what we get is basically is like this triangle is, for example, this is something that we obtained a long time ago, and this was using hyperspectral urban data, and at the St. Lawrence Estuary in Canada, and in here you had the input of the river, very heavily loaded in sediments, and then in here you had like very specific regions where you had the input of the vegetation coming in, and then this is just the mouth of the estuary, which is, I mean, this is like a very evident. I like to use this figure because this is like a very evident type of representation of how the water can be. So in general, when we want to tackle the water quality, or the modeling of the water quality, there are basically two approaches. This is a very simplistic approach, but basically the empirical, so it's statistics, purely statistics, and then you have the semi-analytical modeling, which is far more complex because it's based on the physics of the light interactions, and then you have as well the relationship with the constituents, and it's in here where the artificial intelligent approaches are getting in. So this is just an example of the type of things, of the type of the equations that people use in order to parameterize. In this case, it's based on the sensors to parameterize the different variables that they might be interested in. And as you can see, I mean, they're very, very different, because the type of sensor that we might use is also something that we have to bear in mind whenever we are modeling or we are tackling the water quality of a body, right? Like, because we don't get the same spectral resolution, and the capabilities of the sensors are different, and so basically, just to sum up, what we do is we have the satellite, we correct it everywhere. Like, first of all, I mean, when we're dealing with water, we have to carry out a very careful atmospheric correction. This is something that is paramount, because whereas in the case of the vegetation, the signal is strong enough, so we can work with it. In the case of the water, the signal coming from the water, it ranges between 4% and when it's super loaded with sediments, it can reach the 20%, but it is something that is super unusual. So we're dealing with very feeble spectral reflectances. So wrongly performed atmospheric correction is something that can ruin a study, and it can lead us to very horrendous results or meaningless results. So, well, the next step is just, well, the resampling and the masking, obviously. I mean, when dealing with clouds or land, or, just to make sure that we're just getting the data that we're really interested in, and not something that is polluted by noise in our case. And then the next is just to get the indexes, and we have fun with them, and we analyze them back and forth. And if we have the time series, just the Valhalla, because with that, we can really understand the dynamics of a system. Otherwise, we will be just obtaining a static image of what was the situation in a very specific moment. So, well, this is just if we want to be a bit more complex in the analysis, we can add other sources of information. And the one, is the data that is that the in situ hyperspectral devices provide us, which is great because normally it's under control, and we have a lot more of information that we can get just with the satellite. And then the addition of abiotic variables. So, for example, I don't know, the radiation or the power or there are different things that they can be used, and they are a very valuable source of information that will help us in order to perform a supervised classification, more robust, and so on. So I'm just going to go through like a very I hope I'm not worrying you too much, because I tend to speak too much. But this is just an example.
About 10 minutes, Anna, don't worry.
Okay, so this is an example of all the theory that I just went through before. This is a study that we did in a floodplain lake at the Pantanal of Mato Grosso in Brazil. And it was a very challenging study because we didn't have we didn't have all the elements that we needed to perform a super robust study and to understand better the dynamics, and is an extremely complex ecosystem. Why we did it over there? Because it's part of the world largest wetland that represents 3% of the Earth's humid areas, just something amazing. And the lake in which we focus our attention is the third largest lake within these ecosystems. So we thought, well, we can use it as a sentinel to point out what are the dynamics of the area. So, I mean, this is an area that is subject of flood pulses, and it has erosion, sedimentation, alteration of all sorts of things. They have pollution, aquatic pollutions. They were dealing with biodiversity loss, and well, considering that is within the Ramsar archive, something that we cannot pass the opportunity of studying it. So the first thing that we did, well, considering that the hydrological variability over seasonal and multi-animal timescales we know that determines the structure and ecological functions of the wetlands. Our objectives were very clear. The first one was to understand the system dynamics and to somehow assess the principal drivers of these dynamics and the evolution of the ecosystem. So based on these spectral signature, these are the very general ones, we follow a procedure that is similar to the one that I showed you before, which was basically we focus our attention of discerning the open water, the wetlands part of the images, and the land was there. And we reconstruct all the time series. I mean, a fairly long time series, because our first data is from 1985. We used Landsat, all the Landsat family. And even if in here is reflected 2010, the reality is that we have data up to last year, so 2023. And in order to illustrate the dynamics, these are, I think the best is to observe what happens in the image. And what we have is that for these four images, that they correspond to a very specific period or phase of the water pulse of the lake, we observe that there are at least two moments in which the system, there's quite a bit of a change, the system. So say, well, what's happening? So once that, well, these are the time series that we got. And yeah, we observed these two same periods that we this is the same that we observed in the previous images. We thought, well, what they do correspond. So basically, considering the monthly mean surface area of the lake, we observe these main three phases. And basically what we can conclude is that there's a progressive decrease in the water, even if the after this event around 2000, the year 2000, 2003, the system recuperates, it doesn't reach the initial level of or the initial water quantity that it has originally. So, well, we went through loads of data, and in this case, what we got was we had in situ data regarding the flow, the river flow, and the rain over the lakes. So we tried to understand what was in order to understand the hydrology and the climate over the area. And we performed this type of analysis, which are quite significant. We also went through, well, to better understand in terms of, are we dealing with rainfall anomalies, specifically anomaly data or hydrological anomalies? And it was not that clear. It was something else. I mean, there was just a fringe in which we observed that change, but we have to when further away. So we carry on with the flow difference, and we observed that for sure something was happening between the maximum, I mean the average maximum, and the baseline flow of the different periods. And oh, surprisingly, this period corresponded to the pre-dam construction period. This one is the dam filling, and this one is after the dam, which was, we thought, well, that's for sure. I mean, there's an anthropogenic factor in here, but let's see if it's the only one. I mean, how the climate is playing. Indeed. So for that, we use the indexes, or different climatic indexes, global, and well, we carry loads of analysis in terms of well, the different areas and how the evolution was between the surface area, the vegetation, I mean the wetland vegetation, and so on. And we observe that there was quite a bit of a correlation between two of them, the Niño Modoki and the Trans Niño index. So okay, that's we said, well, okay, that's for sure. I mean, the area has this problem. So it has the anthropogenic problem, then you have the local or the regional scale phenomena, but also the global scale changes are affecting the morphodynamics of the area. And these are like very evident, like the results are quite straightforward, because this first one is one of the largest or one of the most intense La Niña phenomena that had happened in the area, and it barely had a measurable effect over the system. Within this time period, we had the La Niña and a strong La Niña, but it wasn't as strong as the previous one, but it had the added aspect of the dam construction. And then we had a third one in here, which was the weakest compared to the other two, but in terms of the impact, it was the largest. So in terms of change, what we can see is quite terrifying, we can say, because for the first La Niña was a 10% change average. In the second one was a 19%, and then the third one was a 29%. So the trend is quite worrying. So what we can say is that while observing these results, there's a reduction of the system resilience. So the system is not performing, is losing its capacity of recuperating the normal dynamics. And well, this is fine. I mean, we deal with the morphodynamics, but what happened with the water quality? Because I told you before about the water quality, and so I had to jump in this. So what we did was, well, we took an approach that it was purely analytical because we lack in situ data. So we observed the relative changes of the water. And for example, well, this is quite um, um, interesting because we observe the four phases of the water of this system. That is the draw, then it's followed by the rising, and then the flooding, and the decreasing, which is in between, is something that is a mixture of things. So, but we see a pattern of the behavior. But when we compare this, if we do a classification of, well, based on the spectral signature of the same points, what we obtain is that, well, the water is behaving in a very specific way. So there's a dynamic of the water quality. I mean, these are the optical groups that we obtain, and the reddish, the more turbid the water is. So we go from the flooding that is the less turbid ones towards far more complex type of water. So we know that the construction and the filling of the Mansudan and the global climatic events.
I'm sorry, Anna, but we are
Yeah.
over more or less. Just to conclude.
Okay. Yeah. We conclude. So basically, I mean, this is just an analysis of the different variables specifically, and we observe that well, there's for sure the lake is showing as well signs of a region shift, not only in terms of the morphodynamics, but in terms of the water quality. And yeah, these are the limitations. I'm not going to go through it through them. These are the things that they can be done in order to improve these this type of studies. But I leave you to discover them. And thank you very much.
Thank you very much, Anna. Thank you very much. I was while you were speaking, I was thinking on the sarcasm,
Yeah.
and I was also thinking on another problem we're working on is the wetlands and in particular the peatlands in the south.
Oh, yeah.
Ariel is working on them. And of course, one of the things we're interested in the monitoring of the evolution of peatlands. And of course, there are simple things that you can do, but also as you have highlighted, the understanding of what is the phenomenon behind the changes is quite
Mm.
complex. And
Mm.
I don't know if you have any particular advice on how to treat peatlands. Do you have any experience on peatlands in particular?
Midlands are hard to monitor. you, you 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 have poked the it's you have you have poke an eye or something like that. I don't know this expression. It's just, I mean, in terms of the peatlands, what you have to measure, you have to focus on the humidity
Yes.
and changes in the humidity of the area. So basically, because we don't see them directly. I mean, we don't see the extension. I mean, there's no pure water extension of the in the peatlands,
No.
but you have changes in the humidity. So the first thing is to reconstruct those time series. Well, use an index, or not only an index, but a bunch of indexes that can be related to the soil humidity, and then track the changes within a year. To compare them is basically to know the behavior of is like phenological behavior of the area, because whereas around the peatlands the behavior is going to be very specific, in the peatlands it's going to be different, so you can go through it. The problem with the peatlands, I don't know the size of the peatlands in Chile, but in here in Spain, the problem that we have is the size. And they are very small. And we cannot use. I mean, Landsat is super rough. 30 meters, far too much. Sentinel-2 can do a thing. It's not super, but it's the best that you're gonna get. The only problem is that you are gonna have just 8 years of data so far, which is not bad, but it's not super.
Of course.
But there's also, but once that you track those differences between the different habitats, you can use there's now a product that is a combination between Landsat and Sentinel-2. Is actually is I'm not sure if I'm allowed to say it. It's NASA. It's something that NASA has done, and it's an intercomparison between the two sensors. So it's something that is cool because it gives you a continuity, and you have the 40 years of data, and then you can track better what's the average behavior of the system. But in terms of, being very specific and go into detail and so on, Sentinel-2, and thank you.
There is no hope in going into absolute detail. Of course, we are also using Sentinel-1, by the way.
Oh, yeah, sure. Yeah, it's just that I'm an ignorant in terms of radar, but for sure, I mean, the combination, I mean, that was something that I put in the last slide, is the combined use of different types of sensors.
Correct.
Like sensors of different nature. So in order to extract synergy between them. And another thing that you can go through is, you can exploit the temperature, because, and there can be differences between a humid area and a non-wetland.
Yeah, the problem with optical sensors in the south of Chile is the availability of cloud-free images, or at least a small amount of clouds, which is
Yeah.
which is a rare case in the south, where the peatlands are in Chile. Anyway.
Yeah, but in that case, what you can do is a combination. It's a better, I mean, that's something that I use when I deal with, when I tackle For example, the bathymetries, optical bathymetries, and it's a merging of different types of images.
Yeah.
I mean, it's not just one, but a combination of them, and you get the best pixels.
Of course.
So
Very-
it's some sort of a mosaic, Frankenstein, so on. But if the images are are relatively, I mean, they belong to the same period. And when I say the same period, not the same year, but something a little
Jesus.
more narrow than that. You can assume that the differences are basically based on cloud shadows. I don't know, whatever the problem that might be, but and it's something that it works. It does work.
Perfect. We'll continue the conversation offline because we have to close the session now. So,
Sure.
Anna, thank you very, very much for your presentation,
Thank you.
we welcome you either online or here in the near future.
We hope that you can
That
be.
would be perfect. Thank you. Thank you very much.
I'll see you on Monday then.
Te esperamos al
Yeah, yeah.
con.
Okay?
Vale. Nos vemos.
Chao.
Muchas gracias.
Ok, chao, chao, gracias.
Chao, chao.
Muy buena la presentación.
Muy buena.
Sí, muy buena.
El mensaje es muy complejo.
Ese-
Sí, es complejo. Ya estamos fuera, ¿no?